Good afternoon, everyone. Today, I will present our work titled Cave Vehicles, a remote sensing dataset for vehicle detection in aerial imagery. To begin, aerial vehicle detection is a fundamental task in computer vision. It enables the identification and tracking of vehicles from overhead imagery, which is essential in remote sensing applications. These capabilities support important real-world use cases, including traffic monitoring, security and surveillance, and disaster response. Traditional approaches for vehicle detection relied on manual inspection, which is labor-intensive, not scalable, and sensitive to variations in lighting, occlusion, and viewpoint. Now, despite recent advances in deep learning, vehicle detection still depends heavily on the availability of high-quality and diverse datasets. Therefore, developing new and diverse datasets remains essential to improve robustness and real-world performance. Based on these challenges, this work introduces Cave Vehicles, a real-world dataset for aerial vehicle detection. In addition, we evaluate multiple YOLO architectures on this dataset and establish a reference benchmark to support objective model comparison and future research. Now, moving to the methodology, the dataset was constructed following a structured and systematic workflow. This pipeline ensures consistent acquisition, processing, annotation, and organization of the data. Now, starting with the image acquisition stage, images were captured using a Cessna aircraft equipped with a high-resolution RGB camera. The data was collected across diverse environments in Chile, covering a wide range of real-world conditions. These include highways, agricultural areas, residential zones, and industrial environments, ensuring strong environmental diversity in the dataset. In addition, image collection was performed at different times of the day, ensuring diverse lighting conditions. The dataset also includes challenging factors such as occlusions, shadows, reflections, and dust. These conditions increase scene complexity and better reflect real-world detection scenarios. Next, the captured images were processed through a cropping stage. Original images, with an average resolution of 6,000 by 4,000 pixels, were divided into patches of 124 by 124 pixels, using a 50% overlap. All cropped images were then manually annotated, resulting in a final dataset of 15,168 high-quality labeled samples. Now, the final Cave Vehicles dataset contains 15,168 images at a fixed resolution of 124 by 124 pixels. The annotations are provided in YOLO format, with over 63,000 labeled vehicle instances. The dataset is also split into training, validation, and test subsets following an 80-10-10 ratio, enabling consistent and standardized evaluation. In terms of semantic content, Cave Vehicles includes 7 vehicle categories: truck, forklift, machinery, pickup, tractor, car, and bus. These classes cover a wide range of vehicle types commonly observed in aerial imagery, across different environments and operational contexts. Beyond its scale, Cave Vehicles includes several characteristics that increase its realism and complexity. Scenes often contain multiple vehicle categories, with vehicles appearing at different scales, orientations, and positions. The dataset also captures challenging conditions such as shadows, occlusions, and visual camouflage. Additionally, intra-scene variability and diverse environments further increase its value for robust model evaluation. To validate the dataset, we conducted benchmarking using YOLO of 9, YOLO of 10, YOLO of 11, and YOLO of 12. All models were trained using their default configurations for 100 epochs. Results show stable convergence and strong detection performance. In particular, models achieve high precision and competitive MAP values, confirming the learnability and quality of the dataset. At the same time, some challenges remain in complex scenarios, highlighting opportunities for further improvement and establishing Cave Vehicles as a valuable benchmark for future research. Finally, we compare Cave Vehicles with existing aerial vehicle detection datasets. With 15,168 images, Cave Vehicles ranks among the largest real-world datasets currently available for this task. It also maintains a standardized resolution of 124 by 124 pixels, ensuring compatibility with modern deep learning pipelines. Unlike many datasets focused mainly on urban scenes, Cave Vehicles includes diverse environments such as rural, agricultural, industrial, and residential areas. These characteristics position Cave Vehicles as a large-scale and diverse dataset for real-world aerial vehicle detection. Now we acknowledge some limitations of this study. The dataset includes 7 vehicle classes, which may limit fine-grained categorization for specialized applications. In addition, benchmarking focuses on recent YOLO models and does not include region-based detection architectures. Hyperparameter optimization was also not explored, leaving opportunities for further performance improvements. To conclude, we introduced K-Vehicles, a new real-world aerial dataset for vehicle detection. The dataset contains over 15,000 high-resolution images captured from a Cessna aircraft, covering diverse environments and challenging visual conditions. Benchmarking with recent YOLO models demonstrates consistent learning and competitive detection performance, confirming the dataset's value for model development and evaluation. Looking ahead, future work includes extending benchmarking to additional detection architectures, evaluating cross-dataset generalization, and expanding the dataset with new classes and applications in broader remote sensing tasks. Thank you for your attention. We hope K-Vehicles will be a valuable resource for the research community. The dataset, along with contact information, can be accessed through the QR code shown here.